In this lesson, we're going to start examining how we can analyze functions by using some calculus techniques. By analyzing functions, I mean, can we figure out whether they're increasing, decreasing, or they change directions, and things like that. All those ideas depend on calculus because derivatives allow us to figure out the rate of change of different things. So the first thing I want to do is take a look at a graph. When we have a graph, it's pretty easy to figure out where things are increasing or decreasing just by examining it. As we work from left to right, and we usually do want to work from left to right, we can see that the graph is increasing up until we get to this point. So in other words, when we're below an x value of 1, 2, 3, 4, so when x is less than -4, our graph is increasing. Okay. That -4 itself is not really doing anything. It stopped for a second. The next section of the graph, from -4 down, 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 down till we get here, which is -2, is decreasing. Right, so we would say this graph is decreasing from -4 up to -2. Again, we're now at a minimum, so our graph starts going back up again, so it's increasing, increasing, increasing up to 0. So we'd say from -2 to 0, we're increasing. And after 0, our graph continues to decrease. So when x is greater than 0. Now that's pretty easy to do when we have a picture, right? Just work left to right. Is it going up or down? The challenge is, what if we want to do this without the picture? Well, the nice thing is that calculus allows us to do this. We can figure out our gradient function, our derivative, and by using the derivative, we can actually figure out if a function is increasing or decreasing. So for example, let's say we dealt with a parabola, our very basic parabola. We know what that looks like. And let's pretend for a second we don't, but we know it looks like this. Well, using calculus, we can find a derivative pretty easily. And f prime at x would be 2x. If I want to figure out what the function is doing at different points, I can figure out, for example, f prime at -2. If I put a -2 into my equation, I get -4. If I do the same thing for the next one, f prime at -1, I get -2. And we'll just do these like this. F prime at 0, I get 0. F prime at 1, I get 2. And f prime at 2, I get 4. Well, what is this telling me? It's telling me at -2, my function is decreasing pretty steeply. At -1, it's still decreasing. It's a -2, but not as steep. At 0, it's actually a flat spot. It's not increasing at all. At 1, it's increasing at a rate of 2. And at 4, it's increasing even sharper. Well, if you look at what I just drew, it kind of looks like a parabola. So the fact is, by using our derivative and plugging in different points along the way, we can figure out if our function is increasing or decreasing without ever having to draw the picture out. Now, one of the most important points is that point where it changed direction. In our initial picture, we had a couple points where it changed directions. And at that point, it was neither increasing nor decreasing. We call those things turning points, where your function is not changing. It's not going up, it's not going down. We can find those by finding the place where our gradient, our derivative, is 0. In the parabola one, it was f prime at 0. Okay. Each of those points are called maximums or minimums, or turning points, that's okay too. And if we were to draw our tangent at those points, we actually end up with horizontal lines. So if we go back to the very beginning for just a second here, and we would have a horizontal line right here. There's a flat spot in our graph. Doesn't increase or decrease. One right there, one right here. At all of those spots, our derivative would be 0. Okay. Knowing that, well, we can use what happens on either side to figure out if our function is increasing or decreasing. So to identify turning points, take your derivative, figure out where it equals 0, and then choose the value in each interval to determine if it's increasing or decreasing. So just to clarify that a little bit, let's take our function we just did, our parabola. We knew what was happening. Let's take its derivative and make it equal 0. So my derivative is 0. Derivative actually comes out to 2x. You know, put them the other way around so it looks a little bit simpler. Okay, derivative of x squared becomes 2x, and let's solve this. So x is 0. So I know at 0, the function has a min or a max. I don't know which one it is yet, but I know it's got one of the two because it's not changing, it's not increasing or decreasing at the point. It's where it equals 0. To figure out which one it is, I make a little sign diagram. And I say to myself, okay, what's happening to the left of that point? And what's happening to the right of that point? So I'm going to pick a number that fits into my category here. Think of a number that fits into being less than 0. I don't know, -1. Let's figure out if I put -1 into the derivative, what do I get? Well, it's 2 times -1 is -2. In other words, I get a negative. Then I'm going to pick a value that's fitting into this category. I don't know, something bigger than 0. Let's try 1. Let's try f prime at 1. What do I get there? I get a +2. All I care about is the sign here, okay, guys? So this is my derivative. That's what happens when I put a number in there. What is the sign chart telling me? Well, it's telling me my graph is going negative. It's going down. I think it's 0. Here's 0. And then it's going up. Okay? So I can basically draw the picture based on my signs of what that function is doing in different points. And we call this a sign diagram, kind of like you did back in higher functions last year. Okay, the keys here is take your derivative, set it equal to 0, and then solve it. Okay, whatever your solutions are your intervals in your table, okay, where the function changes direction. Okay, there's a couple of different kinds of functions different kinds of turning points you can have. Okay. If you start with a negative sign, decreasing, followed by an increase, well, that means it has a minimum. If your function has an increase followed by a decrease, that means you have a maximum in your sign diagrams. So we're going to obviously make a few sign diagrams today. So let's try some. So I've got some functions. I want to use a sign diagram to find intervals of increase and decrease, and I want to classify any stationary points. So to figure out where my points are, I need to take my derivative. My derivative is 3x squared minus 12x, just our basic power rule. I need to set that equal to 0 and then solve it. So this is common factorable. I'm going to take a 3x out. I'll get x minus 4. So my solutions are x equals 0 and x equals 4. We're solving like a quadratic. So at 0 and 4, something's going on. It's maybe increasing, then decreasing, or vice versa. But at 0 and 4, I've got maxes and mins. So we're going to make ourselves a sign diagram. I'm going to start off by saying less than 0, because that's my lowest value. Then I'm going to say 0 to 4, that's my middle, and then greater than 4. And for each of these, I want to know what happens to my derivative. So let's pick a number less than 0 and put it in. If I put -1 into my derivative, and we'll just do 1 just to show you guys what's happening here, we're going to get 3 times -1 squared minus 12 times -1. Now I don't really care what the number is. It comes up to 15. What I care about is the sign. It's a positive. Okay? I'm then going to do the same thing, but I'm going to pick a number in the next interval. So between 0 and 4. Number 1 would be easy. So 3 times 1 squared minus 12 times 1. Make sure you're using your derivative, okay? This time I get a negative. And if I try the third one, something bigger than 4, let's try 5. 3 times 5 squared minus 12 times 5 gives me 15. In other words, a positive. Well, what have I figured out? I figured out my function goes up, then down, down, and up. So I've got a max and then a min. My max is 0 and something. My min is 4 and something. To figure out the somethings, we go back to our initial equation, because that's how we get points. Our initial point was 6 cubed minus x cubed minus 6x squared. So if I put 0 in there, I get 0 cubed minus 6 times 0 squared. I get 0. So at 0, 0, there's a maximum. If I do the same thing, but I use 4 this time, 4 cubed minus 6 times 4 squared, we'll get 64 minus 96, which makes negative 32. There's my minimum. Those are my stationary points, my points that don't change. Okay. Let's try the next one. We're going to find, and the question said find intervals of increase and decrease. So this would be obviously increasing because it's a positive, as with this. And second part would be decreasing because we have a negative value in our sign table. Okay. Okay, let's try B. We do the exact same things. We're going to do with a different kind of function. A weird kind of function. We call these rational functions because they have letters on the bottom. And we know we don't like letters on the bottom for derivatives. So let's fix that. Bring it up to the top and make it a negative exponent. Okay, same procedure. Let's take our derivative. F prime at x equals 1 minus 100 x to the negative 2. Okay, I want to know where that equals 0. So I'm going to say 0 equals 1 minus. And I'm going to fix the format again just so I can work with this equation easier. So I brought my exponent back to the bottom. Hey, how do I solve this? Well, if I bring the 100 over x squared to one side and leave the 1 on the other side, it might remind you that we can cross multiply. 1 times x squared makes x squared, if we do this way, and 100 times 1 makes 100. So x is the square root of 100. Now be careful here, it could be the positive or negative square root. So we end up with x equals positive or negative 10. And there's one more weird thing that I need to point out to you. Anytime we have an x on the bottom, that's a vertical asymptote, as we learned about in last unit, at 0. When you have vertical asymptotes, that has to become part of your sign diagram, because it's a break in your graph where things change directions. So I actually have 3 parts to this one. I've got my vertical asymptote of 0, plus I've got my 2 points where I think I change direction. So in my sign diagram, I'm going to start off with negative 10 as my lowest point. Then from 10 up to 0, that's my next smallest point. From 0 up to positive 10, and then greater than 10. For my function, my derivative, just to write that down again so it's somewhere close by we can see it, it's 1 minus 100 over x squared. Okay, this equals 1 minus 100 over x squared. So let's see what happens when we pick a number less than negative 10. Try negative 11. Well, if I try that, I get 1 minus 100 over 121. Right, just first one here, 1 minus 100 over negative 11 squared. Well, that's going to give me a positive value. There's an increasing region there. If I pick a number between negative 10 and 0, I don't know, let's try negative 1. We'll get 1 minus 100 over negative 1 squared. That's going to be a negative. There's a decreasing region. If we do the same thing, but we pick a positive number this time between 0 and 10, let's make this positive 1 this time. Well, I still have a negative. And if I pick a number bigger than 10, let's pick the number 11 again, put an 11 in here, I end up with a positive. So the question asked, increasing and decreasing, I can see some of those pretty quickly. Here's an increase, here's a decrease, here's a decrease, here's an increase. And it wants us to classify our stationary points. Well, we're increasing up to negative 10, and then we're decreasing. We're decreasing, and then we're increasing. The only weird thing is, what's happening right here? If you remember, 0 was our asymptote. So if you think about this, what's happening there is what's supposed to happen there. We're going down one side and up the other side. Okay, so that actually makes total sense. We have a maximum at x equals negative 10. We have a minimum at x equals positive 10. We have our axis of symmetry at 0. Okay, so that one's a little more complicated because it had the vertical asymptote in there. For our purposes, your vertical asymptotes will always be 0, and it happens when you have an x on the bottom of a fraction. Okay. There was one more, letter C. I'll bring C down here, take a look at letter C, because there's one more weird thing we need to talk about. So let's do the same thing we did before. I want to find my stationary points. So my derivative has to be equal to 0. So 0 equals, our derivative would be 3x squared. Let's solve this. Divide both sides by 3, we get x squared is 0. Square root of 0, still 0. So in our sign diagram, we have only two sides to it. We have x is less than 0, x is greater than 0. If I pick a number less than 0 and put in my derivative, so let's try -1, I get 3 times -1 squared, which is positive. If I do the same thing, but I choose a positive one this time, I'll get 3 times 1 squared, which is also positive. Well, if I try and draw this, it's supposed to be increasing and then increasing again, but there's no asymptote this time. So I've come across something weird. Okay, what the situation is one that actually looks like this. Okay, and what we say is there's a point right here at 0 and something, in this case it's 0 and 0, where we're changing directions but also still going the same direction. And we call that thing an inflection point. Okay, we are increasing and then we continued to increase, but we went flat for one brief second. Okay, so the example that we just looked at right on the screen here, this is x cubed. Okay, but you could also have ones that go, we're going to decrease, go flat for a second, and then continue on down. And the way we recognize these things in our sign chart is you end up with two of the same signs side by side. But you know that there is no vertical asymptote. Okay? And we don't have that because we don't have the situation where we have something with a letter on the bottom. Okay, so that's our second weird option. So we have the standard one, just a regular old polynomial. Okay, we're going to just do our sign diagrams like normal. We have a vertical asymptote situation. Okay, we have an x on the bottom. And you've got ones where you can get inflection points. They're the weird ones. Okay, we have two signs the same side by side. Okay, last question. We want to find and classify the stationary points, and then we're going to sketch our function. Okay, so just put it all together. So what do we know? Stationary points. That's where our derivatives are 0. Let's find our derivative. Our derivative is 8x minus 3x squared. I want to know where this equals 0. This is a quadratic, so I'm going to solve it as such. I can common factor out the x. I'll get 8 minus 3x. So our zeros, one's obvious, one's a little bit trickier to find, but we can solve for that one. So we get 8/3. Okay, sign diagram time. Less than 0, from 0 up to 8/3, and greater than 8/3. Okay, use our derivative. Let's pick some numbers. Give me something less than 0. -1. If I put -1 into this function for my x's, I end up with a negative. A number between 0 and 8/3. I take the number 1. If I put that in, I get a positive. Okay, make sure you're putting in for this x here and this x, right? We'll get 8 minus 3 in this case. We'll get positive 5. And something bigger than 8/3, I don't know, the number 10. We'll get 80 minus 300. Well, that's definitely a negative. So what's that telling me? It goes down, then up, then down. Okay, so we got ourselves a min at 0 and a max at 8/3. Now, if I want to find the point that goes along with them, I go back to my point equation, which is my initial equation. So let's do that. Our initial equation was f at x equals 4x squared minus x cubed. And I want to know what's happening at 0. That's a nice one. That's just 0. And I want to know what's happening at 8/3. Now, that one's not so nice. If we put that in for x, we'll get 8/3 squared minus 8/3 cubed. Okay, punch it all into a calculator the way it looks. And in some ways, got to work with decimals in this one. You get 9.48. Okay, so back to our sign chart for a second. The min was 0, 0. The max was 8/3 and 9.48. Okay, what's it say? Sketch the function showing all important features. So this extends what we did last unit when we talked about sketching things. Whenever I'm sketching, I need to follow the scale that we're given. So we were told between -2 and +3. So 1, 2, 1, 2, 3. What have we found out? We know there's a point at 0, 0. We know there's a point at 8/3, which is like 2 2/3, and 9.48. So we need a sort of a sense of scale. Let's call this -10 and +10. So 8 2/3 and 9.48, that's a little high there, would be just below that. So let's call it right there. So 8 2/3 or 8/3 and 9.48. So those are my turning points. What else would be considered important? Well, probably if we had zeros, that might be important. How do we find zeros? Well, that's where our original function equals 0, right? Now, I'm totally fine if you guys use graphing calculators for this stuff. Not a big deal. We end up with solving this quadratic. X is 4 and x is 0. Now, for our purposes, we already graphed the 0, 0, 1, and this is beyond our domain. So it doesn't actually matter for our question. We're only supposed to graph from -2 to 3. All right, so what do we got? We got our graph was going minimum here, maximum here, and then going down. Oh, we shouldn't put an arrow on the end, right? Because our graph is going to stop over here. That's our boundary. And we know this one's going to go up. Again, we don't know how high it is. So we'll put an arrow up dot on the end to say that's the end of our boundary. I'll fix my lines here. Okay. And then we got ourselves a brief description of how this looks. Now, because they give us boundaries, we should actually label these points. This would be -3. And if you use your original function to figure out the y value that goes with it, you get approximately 24. Actually, that's not -3, sorry. It's -2 and 24. If we try the 3 one, we get 3 and 9. Okay, and then we get a brief idea of what this graph looks like in the domain that we were given the graph. Okay, so just to review some key concepts from today. If you want to know whether a function is increasing or decreasing, take your derivative, set it equal to 0. That will tell you where the stationary points are. On either side of that, it must be increasing or decreasing. And we can use that to make a sign diagram. Okay, try a couple questions. Make sure you can do these ones. And if you're stuck, come see me and we'll figure it out together.